Okay, for this problem we have a random variable whose PDF is 2 times x, where x goes between 0 and 1. The question is to find the moment generating function for x, and then we need to directly use the moment generating function to find the expected value of x. Now, it's kind of silly to use the moment generating function to find the expected value of x because the expected value of x is very easy to compute for this PDF, but we will use, the problem asks us to use that technique instead. So first off, the moment generating function. That's the expected value of e to the t of t times x. So in our case, integral from 0 to 1, e to the t times x times the PDF 2x dx. And whatever that is going to be the moment generating function. All right, to do this, we get the integral from 0 to 1. Let's write this as t times e to the tx times 2 over tx dx. And the reason I do that is because the thing in parentheses is the derivative of e to the tx times 2 over t times x dx. So applying integration by parts, we get e to the t times x times 2 over t times x, evaluated from 1 to 0, minus integral from 0 to 1 of e to the tx times the derivative of this with respect to x, which is 2 over t dx. Okay, so I'll evaluate on the next step e to the t times x times 2 over t times x. Then the antiderivative of this will be 2 over t squared e to the t times x. And we evaluate this between 1 and 0. And I'm plugging in for x, not t. Okay, so everywhere I see an x, I replace by 1. I get e to the t plus times 2 over t minus 2 over t squared e to the t. Then everywhere I see an x, I replace by 0, so 0. And then over here I have minus 2 over t squared. And so finally that means the moment generating function is equal to, let's see, I can write everything over t squared. And so that's going to be 2 times t times e to the t from this part. Then I have minus 2 e to the t from the middle. Then minus a minus becomes plus 2. And so that is the moment generating function for this random variable. Now, to find the expected value from this, we use the property. Now, this is why this is called the moment generating function. The expected value of x is equal to the derivative of the moment generating function evaluated at 0. So let's compute the derivative, and then we plug in 0. So let's compute the derivative, and we get, well, let's see, derivative of the top will be 2 times e to the t plus 2t times e to the t, using the product rule on this, minus the derivative of 2 times e to the t is the same thing, 2 times e to the t, then plus the derivative of 2, which is 0. So that's the derivative of the top times the bottom, minus the top times the derivative of the bottom all over the bottom squared. All right, so let's simplify this and hope for the best. So these two terms here, if I take the middle and the t squared, that's 2t cubed e to the t. Then here I have 2e to the t and minus 2e to the t. Those cancel. And so the first term just simply is this, minus. Okay, then I'm going to multiply all these by 2t. So I have 4t squared e to the t. Then minus a minus becomes plus 4 t e to the t. Then minus 4 times t over t to the 4th. And I can simplify a little bit by canceling a t out, so I get 2t squared e to the t minus 8t e to the t plus, I'm just canceling t out, so that should be 4t e to the t plus 4 e to the t minus 4 all over t to the 3rd. So that is the derivative of the moment generating function. Now I need to plug in 0. Well, clearly I can't just simply plug in 0 because that would be a 0 in the denominator. Also, if I plug in 0, this would be 0, this would be 0. If I plug in 0, that's 4 times 1 minus 4. So if I try to plug in 0, it's 0 over 0. So I need to use L'Hopital's rule to figure out what the limit of this function is as t gets close to 0. So applying L'Hopital's rule, let's take the derivative of the top and divide by the derivative of the bottom. Derivative of the top is going to be 4t times e to the t plus 2t squared e to the t. That's derivative of this first bit. Second bit, minus 4 e to the t minus 4t e to the t. That's the derivative of the second. This term is plus 4 e to the t when I take the derivative. And I divide by 3t squared. Okay, now let's see. How can I simplify this? Well, this cancels this. Also, this cancels this. So that leaves me simply, limit as t goes to 0, of 2t squared e to the t over 3t squared. And clearly t squareds cancel. And so now I can take the limit as t goes to 0. So I get 2/3 times 1, which is 2/3. Okay, so that is the expected value of x. Now, as I said at the top, it is really silly to do the problem this way because the expected value of x could be directly computed from the PDF. Let me just do that real quick. So this was not asked in the problem, but the expected value of x, using the techniques from earlier in the semester, would be integral from 0 to 1 of x times 2x dx, which is integral from 0 to 1 of 2x squared dx, or 2/3 x cubed from 1 to 0, which works out to be 2/3. So certainly the moment generating function approach gives the same answer, but it's a little bit longer. For some functions, it's easier to use the direct approach. For some, it's actually easier to use the moment generating function approach, believe it or not.